So you were recently assigned 4 related rates problems, and I'm going to run through the solutions to those here. In problem 1, a hypothetical square grows so that the length of its sides are increasing at a rate of 6 meters per minute. How fast is the area of the square increasing when the sides are 9 meters each? Okay, so this is a related rates problem, and we have a strategy for addressing this. We start by drawing a picture. I'm going to draw a picture of a square because that's what this problem happens to be about. This is as close as I can get to a square here. It's growing, so it's getting bigger, right? So things are heading in this direction. So I like to indicate how things are changing in some way there. This thing's growing. The sides are increasing at 6 meters per minute. So the sides are changing. So I label the things that are changing with a variable. And since this is a square, these are all x. And they're telling us that the rate at which those sides are increasing is 6 meters per minute. So they're telling us a derivative, right? Rates are derivatives. The derivative that they're telling us is dx over dt, the derivative, the rate of change of x with respect to time. So dx over dt is growing at, or increasing at 6 meters per minute. So that's a positive 6. And then we're concerned with how fast the area is growing. Well, I haven't indicated it on here yet, but right, this area inside here is also changing. Anything that's changing gets a variable name, a variable. And they want to know how fast the area is changing. So that's a question there. That's the thing we're supposed to find out. dA dt, right? We're trying to figure out how fast the area is changing. And at that point in time, the sides are 9 meters. So we draw a picture, we label things that are changing with variables, we make a list of all of the information from the written problem, the numerical information, and we make sure we know what we're trying to find, right? We are trying to find the rate of change of the area. How fast is the area of the square increasing? So you get all that down, and then what we need is a formula so we can do our calculus. We need a formula that relates the area to the sides of the square. And we all know that famous formula is A equals side squared. For us, that's x squared. Once you have the formula, it's time to do derivatives. So we do the derivative with respect to t. So the derivative of A is 1 dA dt. The derivative of x squared is 2x times dx dt. We always follow the chain rule when we do the derivative implicitly. Now, once you have your implicit derivative written out, it's time to evaluate, and that means plug numbers in. So I'm going to plug that 9 in where this x is, and I'm going to plug the 6 in where the dx dt is. And I'll just multiply that out. So Ra equals 2 times 9 times 6. That's 12 times 9, that's like 108. And that is meters squared per minute, because area is measured in square units. So 108 meters squared, oops, made a mistake there, meters squared per minute. Let's take a look at number 2. Water slowly evaporates from a circular puddle. The radius of the puddle decreases at a rate of 6 inches per hour. Assuming the puddle retains the circular shape, at what rate is the area of the puddle changing when the radius is 13 inches? Okay, so we've got a puddle. This is a circular puddle, right? It's going to maintain its circular shape. Oops. So let's draw the puddle here. Now this puddle is not getting bigger, it's actually getting smaller, which is hard to draw, but I'll just draw my arrows pointing in, letting you know that this thing is shrinking. And this is the most interesting evaporation I've ever heard of, but it's actually going to shrink in towards its center for the sake of this problem. Okay, now as that circle changes, its radius changes, and so does its area, which is the stuff inside that circle. So we know that the radius is changing at a rate of, it's decreasing at a rate of 6 inches per hour. They're telling us the rate of change of the radius, so that's dr dt, that's the derivative. It's decreasing, so that's negative 6 inches per hour. And we are asking at what rate the area is changing, right? At what rate? So they're asking us for dA dt. That's what we're trying to find. Very similar to the last problem. And we're looking for that rate at the time that r equals 13 inches. So just like the last problem, we need a formula that we can do the calculus on. In this case, we need to relate the area to the radius. So your geometry teacher probably taught you a famous formula, which is A equals pi r squared. That's the formula for the area of a circle in terms of the radius. Once we have that formula, we do our calculus. So the derivative of A is dA dt. We use the power rule to get 2 pi r, and then don't forget the chain rule, dr dt. And at this point, it's time to evaluate. So our radius is 13. I'll plug that in here, and I'll put negative 6 in here. And when I do that, I get dA over dt, the rate of change of the area, equals 2 times pi times 13 times negative 6. And that's going to work out to be about negative 156 pi. And that's in inches squared per hour. Square inches per hour. So 156 pi, and then if you want to know the decimal value for that, you can multiply this out. But it's negative because this circle is shrinking. Negative 156 pi inches squared per hour. That's it for number 2. Let's take a look at number 3. Number 3 says a perfect cubed shaped ice cube melts so that its length of its sides is decreasing. It's decreasing at a rate of 3 millimeters per second. Assume that the block retains its cube shape. We've heard something similar to this from the last problem. At what rate is the volume of the ice cube changing when the sides are 2 millimeters? So very similar problem to the last one. It's just that it's about a cube instead of a square. Instead of a circle. So let's see if I can draw a cube without knocking everything around on the screen here. I'm not talking because apparently I need to concentrate when I'm drawing this cube. Okay, so hopefully that looks kind of like a cube. Remember, with a cube, all the sides are the same. So this thing is shrinking, right? It's melting. And it's changing at a rate of, where the sides are changing, decreasing at a rate of 3 millimeters per second. But I don't have the sides labeled with a variable s. So let's just call them all x. And they're all x because it's a cube, right? In a cube, the measurements are all the same. So oh goodness, what just happened? So the side length is changing at a rate, so the dx dt is 3, but it's negative because it's decreasing, millimeters per second. At the time we're interested in, the sides are 2 millimeters, so that's x equals 2 millimeters. And we are trying to find the rate at which the volume is changing. And the volume, remember, is in here. That's dV dt. That's the thing we don't know. So we drew our picture, we labeled our variables, we got organized by listing our information, and we've identified what we're trying to find. Now we need an equation that relates these variables. Well, this is a less common formula, but the volume of a cube is just x times x times x. And so that's just going to be x cubed. Once we get that formula, you know what we do. We take the derivative. So this is dv dt equals 3x squared, and then don't forget the chain rule, dx dt. Okay, I think we're ready to plug some numbers in. Let's see what we've got here. I'm going to plug in 2 for x, and for dx dt, I'm plugging in -3. So basically, this is going to be dv dt equals 3 times 4 times -3, so that's -36, and that is cubic millimeters cubed per second. -36 millimeters cubed per second. How do you like my millimeters there? It just looks like a big long squiggly line, but it's supposed to be two m's next to each other. Okay, and that's it for that problem. You kind of see a pattern with these. They do get more complicated, but we're just trying to get used to this related rates process. Draw the picture, label the things that are changing with variables, list your information to get organized, come up with a formula or steal it from a formula sheet, take the derivative, plug in the numbers. Now number 4 is a little more complicated. It has to do with a container holding liquid. So let's move on to number 4 and we'll talk our way through that one. It says a conical paper cup, and conical is implying that the shape is a cone. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The bottom of the cup is punctured so that the water level goes down at a rate of 2 centimeters per second. Remember, that's a rate there, and that's for the water level. At what rate is the volume of the water changing when the water level is 7 centimeters? Okay, so let's start by trying to draw this picture. This picture actually has 2 cones. There's the cup itself, which is shaped like a cone, and the radius is the same as the height. So I'm going to try and draw this as 10, and I can label that 10 right on the picture because it's constant. And then this is also 10. So this height here is 10. Now inside that cone there's water, right? So that's in the shape of a cone as well, a similar figure. It's proportional. And the water is trickling out the bottom so that the water level is decreasing. Now that water has some changing measurements. Its radius is not always 10, so we're going to label that with an R. And its height is not always 10, so we're going to label that with an H. And then we're going to get organized by listing our information. So we're told that the water level, the dH dt, is decreasing at a rate of -2 centimeters per second. If it's going down, it's decreasing, it's negative. At the time we're interested in, the H is 7 centimeters, and we're trying to find out at what rate the volume's changing. So dV dt is what we're trying to find out. And remember, even though it's hard to label it in here, the volume is, I'll label it with this green V, it's the amount of water inside there. Okay, now normally in geometry class, you'd look up the formula for the volume of a cone, and you'd see V equals 1/3 pi r squared h. That's the formula from geometry class. Or you might see it as pi over 3 r squared h, or pi r squared h over 3, some form of that. The problem is all of our information down here is in terms of just V and H. So we don't know anything about R right now. That's where this container comes in. The container shows us the relationship between the radius and the height. And lucky for us, those are equal. The radius always equals the height. It's not always that case, but for this first time that we're doing this, that's our situation. That means that I can replace this r squared with an h squared. And so I can rewrite my formula before I take the derivative as 1/3 pi h cubed, because h squared times h is h cubed. And then we can go ahead and do the implicit differentiation right on this formula. And we get dv over dt equals, when you bring the 3 down with the 1/3, that makes a 1. So that's pi h squared Then you have to multiply by dH dt. And just like the other problems in this assignment, we're ready to substitute in numbers. So we're going to evaluate h at 7 and dH dt at -2. And we end up with 49 times -2. That's going to be -98 times pi. So dV dt is -98 pi. And that's volume, so that is centimeters cubed per second. And if you could tell, I was stalling there a little bit because I had to look up here and see what the units were. The linear measurements are measured in centimeters, and the time is measured in seconds for this problem. So that's why our label is cubic centimeters per second. So that was 4 related rates problems. Those are introductory level problems. This last one, we did have to use the relationship between the radius and the height to eliminate variables, which is something that comes up from time to time. So be ready for that. But this is pretty good for a first try at related rates problems. If you have any questions, you know where to find me. And in the meantime, take care.